Welcome to my YouTube channel. I am Arthur Francis Diban. Welcome to AFD'S Academy. Today we're going to be dealing with physics, and in today's work we're going to be discussing on how to arrange our resistors in series and parallel. Now, in the topic current electricity, where we have volume or voltage equals to IR. I is for the current, R is for the resistor, or the resistance of a capacitor or of the inductor, whatever it is. So if we are to calculate our voltage effectively, V equals to IR, we must determine many a time the arrow will be given to us in series or in parallel. So that, as little as it looks, may become a big problem if we do not understand how to do that little calculation before we can commence in the application of the formula in its entirety. So our work today is going to be focused on how to deal with the resistors in parallel and in series. So I'm going to give us a practical overview on how to do that. Then we can solve a couple of questions in respect to that phenomenon. So there is physics, parallel, okay? Resistors and series. Series arrangement. So parallel resistors and series arrangement. So we're dealing with the resistors in parallel and in series. So first, an example, illustrative example of that. When we talk of resistors in series, we're saying total resistors is equals to R1 plus R2 plus R3 and so on. The resistors may be quite more than this, right? Then it therefore means that if a question is being given to say there are three resistors of resistance 1 ohm, 2 ohm, and 3 ohm. Calculate the effective resistance or resistors in series. This is the formula. In series means that we're going to add the first resistor, the second one, and the third one together. That is what series means. Therefore, our R total will be 1 plus 2 plus 3, which is equals to 6 ohm or ohms. So this is just a practical example of what series arrangement is. But if we are being asked to arrange the resistors of resistance in parallel, it therefore means that the arrangement differs. This is how it will be. That we say in parallel is 1 over R becomes 1 over R1 plus 1 over R2 plus 1 over R3. Alright? So if the resistors of resistance are 1 ohm, 2 ohm, 3 ohms, etc., we shall arrange them in parallel. We will now have 1 over R, which is 1 over 1 plus 1 over 2 plus 1 over 3. Now, if this is the case, we've gotten this, we have to proceed further because we're not going to stop here. So we're going to take total the LCM of the denominators as stored in mathematics fractions. So the LCM of 1, 2, and 3 is 6. 6 can divide this, can divide this, can divide this. The lowest number that can do that. 12 can also, but it's not the lowest, even 24. So 6 here, 6 divided by 1 is 6. 6 times 1 is 6. Plus 6 divided by 2 is 3. 3 times 1 is 3. Plus 6 divided by 3 is 2. 2 times 1 is 2. So this, remember, we have 1 over r, which gives us this. So 1 over r will become 9, 10, 11 is 11 over 6. The inverse of this becomes 6 over 11. Or, if you don't want to use the word inverse, let's go back this way. We now have 1 over r is equals to 11 over 6. I want to make r stand out as the subject. R times 11, I have 11r is equals to 6. If I go start by 11, 1, 1, 11 cancels itself, r is equals to 6 over 11. So, by so doing, I've been able to get my r in parallel, and the value is 6 over 11. So, it's either when you're here, you just say the inverse of this, which is 1 over the inverse, the reverse, it becomes 6 over 11 to stop the whole story there. Let's take practical questions. Now, I've been able to give us an illustrative phenomenon of what series arrangement of resistors is and parallel. But what about their diagrammatic representation? How then are we going to know when something is in parallel or it is in series? So let's check that out before we proceed. Now, this Alright, these are my resistors, R1, R2, R3. This is the symbol of resistors, and this is what it means that when they're in series, they look in this manner. But when they're in parallel, for example, we have something like this. And this is R1, this is R2, and this is R3. These ones are in parallel to one another. So these are series arrangements and these are parallel arrangements. Why am I taking my time to bring this up? Is because maybe from our next question I have to, when I bring any question that has to do with this diagram, we're not going to be confused. We'll know exactly what we're referring to or what we meant. So let's take another question. This is more of a practical question. All right, this is a question. Let's see what it says. It says we should calculate the effective resistance between P and Q in the diagram shown above. Now, in this diagram, we should calculate what the effective resistance, which means, remember, from this diagram, we understand that these two are in parallel. If we collapse them as one, that will be in series with this. So for us to get effective resistance, which means the total resistance of the resistor, means therefore we have to calculate our parallel resistance, keep them together, and add with that of the series, thereby get our total what? Resistance inside the system. So let's start with this. I will start by saying 1 over R is 1 over 2 plus 1 over 2. LCM, 1 over R is equal to the LCM here is 2. 2 divided by 2 is 1. 1 times 1 is 1 plus 2 divided by 2, 1. 1 times 1 is 1. So 1 over R is equal to 2 over 2. The reverse is the same thing as 2 divided by 2, which is equal to 1 ohm. So now we've got to that to be 1. The parallel resistance gave us what? 1. So we'll add that with series. Now R total will be that of series, which is 3 ohm, plus that of parallel, which is 1 ohm. And this is 4 ohms. So this is it. The effective resistance is that. Calculate the effective resistance between P and Q in the diagram shown above, and our answer is 4 ohms. We're going to take another question. We're going to solve a couple of questions so that we can see how to go about it when it comes to resistors in parallel and series. Now, let me take this out. It said a parallel combination of 3 and 4 resistors is connected in series with a resistor of 4 ohm and a battery of negligible resistance. That we should calculate the effective resistance in the circuit. That is a WIEC question. So let's see again. We say we should calculate a parallel combination of 3 and 4 resistors connected with 4 of series. Now parallel, remember 1 over R in parallel of 3 and 4, so it becomes 1 over 3 plus 1 over 4. A parallel combination of 3 and 4 is connected in series with 4 ohm. So this is series of 4. So if I'm done with this parallel, I now have to add with that and proceed to get my total effective resistance. So now this is 1 over R is equal to the total resistance, LCM of 3 and 4 is 12. 12 divided by 3 is 4, 4 times 1 is 4, plus 12 divided by 4 is 3. 3 times 1 is 3. So 1 over R is equal to 7 over 12. R, the inverse, is 12 over 7. Now, I'm adding that with 4 plus 4. The LCM here is 1. Alright? I'm adding with that of the series. I'm done with the parallel, which is 12 over 7. I add with that of the series, which is plus. And now my LCM here is 7. 7 divided by 7 is 1. 1 times 12 is 12. Plus 7 divided by 1 is 7. 7 times 4 is 28. Come over here. 12 plus 28, that is 40. Now, R is equals to 40 over 7. R is equals to what? 40 over 7, 5.7. So this is 5.7 ohms. That's our next question there. So let's take another one. Now, okay, let me take out this. I guess we do not have any problem with these series and resistors. How we collapse that of the parallel resistors to merge them with that of series, all right? That is how the trend goes. Sometimes we may start with that of series. When we are done with that of series, we now merge them with parallel, as the case may be. We add the effective of series effective resistance of parallel, total, we bring them together and we proceed. Okay, let's take this. I have this. Okay, 4 ohms, 4 ohms, 4 ohms. So these are the resistors, all of them, 4. 1, 2, 3, 4, 5, 6 of them. Now, they are asking, find the effective resistance in the diagram above. This is the diagram, the effective resistance. Now, the question is, are these resistors in parallel or are they in series? Right? So, if they're in series, I showed you how we come with a link, blend, then we see that all of them are connected to one current passing through. But this one is not like that. If they are in parallel, I mean. But now we can see that they're in series. Each of them will have its own connection if the case may be of voltage and current and so on and so forth. So we call these ones to be what? In series. So if they're in series, now what is the effective resistance? We say R total will be 4 plus 4 plus 4 plus 4 plus 4, 3, 4, 5 plus 4. 4 times 5, 24, 6, 24. So this is 24 ohms. So because they are what? In series. So we just add all of them together. All right, let's take another question. Two resistors of resistance 6 ohms and 4 are connected in parallel. 6 and 4 are connected in parallel. A third resistor of 8 is then connected in series with a parallel connection. Calculate the effective resistance of the arrangement. All right. Now we're going to deal with that of parallel first, then we'll bring that of the series and merge. All right. They say two resistors of resistance 6 and 4 are connected in parallel. 6 and 4. So 1 over R, 6 and 4. And all of these are connected to a series of 8. So I'll bring that. So 1 over R is equals to 6 times 4. Okay? It's 24. Let's take that. Our LCM is 24. Now 24 divided by 6 is 4. 4 times 1 is 4. 24 divided by 6 by 4 is 6. 6 times 1 is 6. So 1 over R is equals to 10 over 24. R total will be 24 over 10. Now, it's either we divide it and add with 8. If we want to find the total here, we have 24 over 10 is the same thing as, let me say, 24 divided by 10 is equals to 2.4. So I will now say my R is equals to 2.4 plus the 8 that is given, and this becomes 10.4 ohms. It's either you do it this way, you're correct, but you can still move on from here. You can come over here. Let's take another option. We have 24 over 10 plus 8 over 1. Our SN here is 10. 10 divided by 10 is 1 times 24 is 24 plus 10 divided by 1 is 8. Yes. 8 times, 10 divided by 1 is 10. Yes, 10 times 8 is 80. So this is 80, 90, 100, 104 over 10, which would be the same 10.4 ohms. So in my opinion, this one is quite okay, but this one you have to still apply some other much work to be done. So you can just take this method and you move on. All right. Let's take a couple of more questions. Okay. Okay. Now let's look at this. These two questions are in parallel to each other, but this and this are in series with each other. So it therefore means that we're going to calculate this in parallel, then place it down here, thereby the three of them will become what? In series. So first of all, let's do with the parallel, okay? Which is this two. So I have 1 over r is equals to 1 over 10 plus 1 over 10. My LCM is 10. 10 divided by 10, 1 times 1 is 1 plus 1 here 2. 1 over r is equals to this. 2 over 10. The inverse of that is 10 over 2, which is equals to 5. So if we collapse this, we are going to get 5 here. So now let's assume that we are now having 5, all right? We have calculated these 2 and we have our 5. So now we're going to add in series, this, and this. So in series we have our R equals to 10 ohms plus 5 ohms plus 10 ohms. And R is equals to 25 ohms. So this is it. So from that diagram upward, our effective resistance is 25. Okay. Let's take another question. Which of the circuit illustrated here will give us a total resistance of 1 ohm? So we have about a couple of them. We're going to be solving them, all right? We'll solve them until we get the one that has 1 ohm. When we get the one that has 1 ohm, we stop. So let's begin. So our first one here is 236. So which one will give us 1 ohm as our effective what resistance? So we don't know until we solve them. So these ones are in series. In series means R is equals to 2 ohm plus 3 ohm plus 6 ohm. That is 6, 7, 9, 10, 11. R is equals to 11 ohm. So of course it's not this. So this is out. So here we say this one is wrong. It's not giving us 1 ohm. Let's proceed and take another one. The next one is this. And this is 3 and 3. So let's see if this one will give us, but these two are in parallel. So let's see if we're going to get 1. So we have 1 over R is equals to 1 over 3 plus 1 over 3. So 1 over R is equals to, our LCM here is 3. 3 divided by 3 is 1. 1 times 1 is 1 plus 3 divided by 3 is 1. 1 times 1 is 1. So this gives us 2 over 3. The inverse is R is equals to 3 over 2, which is equals to 1.5. So that one too, this one too is not correct. It's not the right option. We're going to take another option. The third one, 236. Okay, this one, they are all in parallel. So we have 1 over r is equals to 1 over 2 plus 1 over 3 plus 1 over 6. 1 over r is equals to LCM is 6. 6 divided by 2 is 3. 3 times 1 is 3 plus 6 divided by 3 is 2. 2 times 1 is 2 plus 6 divided by 6 is 1. 1 times 1 is 1. 3, 5, 6. So 1 over r is equals to 6 over 6. The inverse r is equals to 1. So I think this is our solution. That's where we start. So that's our third question. So we cannot continue solving. There are other ones which we can, but let's stop there for the time. And I think we can solve many as we can, but let's just take one more. Yeah. Which of the following arrangement will produce an equivalent resistance of 1.5 from 3 1 ohm resistors? So let's see. There are 1 ohm resistors, 3 of them. Let's take this out. So our first question is all in series. In series, we say R is equals to 1 plus 1 plus 1. R is equals to 3 ohms. So this is not it. It's not it. It cannot give us 1.5. Let's take our next question and see. So A is out. Let's take B. Okay, this is our next question. So if we are to solve this, I think from my understanding, this could be our answer. But I'm not going to solve it. This one should be like assignment to you. Try and see if you're going to get what is that 1.5 ohm. If you get 1.5 ohm, go to the comment section and comment how you did that. All right, the steps in which you took in order for you to get a 1.5. If you're unable to get that, you can still let us know so that we can still solve it any other time, or I can just let you know how that can be done. Okay. So today, what we've done is just a review of how we can get our effective resistance in a resistor, okay, which is either use the parallel or the series method to do that. The reason why we have to understand this first is because we can proceed from here further to get our, how do you call it, our voltage, V equals to IR, which that is IR, where I is the resistance of the resistor. Then I is the current, this is the volt, potential difference in volt. So this is the formula we use in Ohm's law, but since the resistors are most times in series or parallel, our knowledge of understanding how to do that becomes very important, because if we're unable to do that, we cannot apply that when we're dealing with this formula. So that is why today I'm taking my time to show us this. Part 2 of this in physics could be our current electricity generally, where we're going to solve a whole lot of other questions. So Our lectures will always go across physics, chemistry, maths, and maybe sometimes we can go into biology, as the case may be. But what is most important is you subscribing, because if you do not subscribe, we don't get these lectures, and a whole lot of stuff will be passing you by. So I will encourage you to subscribe and press the subscription button, the notification bell, so that all of these which we do will get to you. Thank you. Have a nice time.